Sí, dale, gracias. Nunca lo pondré. Está bien.
Sí, pero él lo subió. ¿Qué hice del de? No, perdón,
Doctor María. Hola, ¿qué tal?
Gusto. ¿Conoce al doctor Francisco Hernández?
Ah, claro que sí.
¿Usted fue su
Asesor, sí, sí.
asesor? Ah, qué chingón.
¿Entonces de Navidad?
Sí, era mi super cuate de CIMAT. Sí, desde que estaba en prepa yo tenía ahí como cositas de ferias de ciencias. Sí, y San Francisco me hizo paro en varios proyectos. Sí, siempre me ha hablado de usted. Y que luego vino un taller, ¿no? No sé si este año o fue el año pasado. De que eras una cosa así, ¿no?
Sí, una cosa de
Sí. A cada rato va, ¿verdad? A Guanajuato. ¿Ese güey?
¿Yo?
Francisco.
Ah, Francisco sí.
Sí, Francisco va.
Sí, el esposo es de Guanajuato.
Ah, sí, cierto. Que ya tiene 2 hijas y todo.
O sea, tiene niñas y cuando pueden, pues van a
Sí.
dar una vuelta a Guanajuato.
Sí. Ah, qué chido. Sí.
¿Entonces dónde estás tú ahorita?
Estoy ahorita en el DEMAT, en UG.
Ah, no.
Sí, está allá. Yo estoy allá, pero este año que pasó estuve en la facultad de mate de la UADY, de Yucatán, y pues como que me iba todo lo del CIMAT y pues ya como que tenía el back, o sea, ya el contacto y pues estaba chido. Y pues ya hasta fue ese semestre que me transferí. Sí, estaba, exacto, está chido, pero el pinche calor sí está. Y a mí no me gustaba que no haya como tan chido el convenio de CIMAT y la UADY. Como que la UADY es muy, como eran más, se volvieron muy políticos y ya. No sé, como que no me sentí tan. Exacto. Sí. Y pues como yo igual tenía cuates egresados de ahí, así, que de hecho están aquí en el evento, y conocí igual durante prepa, yo creo. Pues ya como que me fueron metiendo ideas y todo, pero pues ya anda ahorita ya en Guanajuato. Sí, en Máxima. Sí, está bien chido.
Oh, qué bueno. ¿Qué viniste
Sí, pues ya desde el año pasado quería venir, pero pues no pude. Pero pues ya fue hasta ahorita. Y como estaba acá cerca de Guanajuato, pues ya no había pretexto. Ya no había pretexto para. Sí, oye, sí, de hoy es el de Benjo y.
No sé, ¿qué va a pasar por ahí?
Sí, de acá de ver al doctor.
¿Él va a ir a Guanajuato otra vez? ¿Va a ir a...
Ah, Jorge Musel. Ah,
sí, va para enero,
octubre, ¿no?
En octubre, sí.
Sí, porque está el taller de Deep Learning. Ah, y también va a estar Aaron Corby, sí, de Chicago. Sí,
acá en enero, o el año pasado, ya no me acuerdo. Creo que fue en enero.
Ah, pues qué chido. ¿Qué más conoces allá del CIMAT Mérida?
Pues no preguntan todos, no me acuerdo los nombres.
Ok, pues está Omar Muñiz, hace como análisis funcional, es un calvito que habla chistoso y siempre está sonriendo.
Omar es después, yo creo que tiene la primera generación de...
No.
Sí, hermano.
¿Joel Trejo?
Joel Trejo.
Sí. El doctor Adolfo, nadie conoce al doctor Adolfo. Nadie lo conoce. Sí, es bien chido el doctor Adolfo. Sí, ¿él suele venir a Guanajuato?
Sí, pero viene
poquito, ¿no?
Sí, viene y se hace un vuelto. Y es bueno, el coordinador que ya dice que quiere que manden a otro más.
Sí.
Estás en el...
Sí, sí. Sí, a veces sí lo veía muy atareado el doctor. Se echaba sus chambas.
A mí me gusta ir a Mérida, pero la verdad que es que voy bajo calor.
Sí.
Que en enero es un buen clima, ¿no?
Pues buen clima. O sea, es que en diciembre, enero y febrero, pues viene siendo como 25 grados, 23 grados. Y en la noche 22, sí, es normal. Pero solo 3 meses. Ya el resto de... Cuando llueve, ¿no? Pinche bochorno. Ajá. Es que ahí el aire está hirviendo. Así que pues es lo que... Sí, sí. Está chido para vivir. Está chido para vivir. Quizás. Hay muchas comunidades. Sí, sí. Sí, está. Pero está un poco aburrido, a mi gusto. Bueno, quizás porque soy de ahí. Pero sí, pues. Por ahí ando.
¿De allá eres?
Sí, soy de Mérida. Pues estoy allá y todo el rato, pero pues ya está dando.
¿Y ya te viniste?
Ajá. Sí, ya. Transferencia al de mat. Sí, sí, o sea, ahorita de mat. Ya de hecho la otra semana me credencial. Lo que todavía no me dan es el correo de CIMAT.
Ah, tú acabas de entrar ahorita, ¿verdad?
Sí, sí. Sí, o sea, ya está en la facultad de matemáticas.
Sí, sí, sí. ¿Estás en la facultad de ella?
Sí.
¿Y te viniste de intercambio un semestre?
No intercambio, ya de plano. Voy a terminar
mi
licenciatura, ajá.
Ah, ok.
Sí, sí.
¿Cómo qué semestre ibas allá?
En segundo.
Ah, yo en segundo.
Sí, sí.
¿Y empezaste de cero acá o te
Todavía no me dicen, pero por mientras estoy yendo a las clases del primer semestre. Pero en teoría, creo que las únicas que me pueden revalidar son dos: cálculo 1 y álgebra superior 1, que aquí es matemáticas elementales. Sí, porque las que tuve en el primer semestre no. O sea, es que ahí no todas las prepas llevan cálculo, solo 3 prepas llevan cálculo. Y pues el primer semestre es como que trigonometría básica, cosas así. Sí me fastidió un poco. Pero ya el segundo semestre, como ya empieza la licenciatura. Así que pues, a ver. Sí, pues a ver, todavía no empieza lo feo del semestre, así que empiezo a ver cómo está. Sí, pues un gusto. Ahí estamos viéndonos.
Claro que sí. Saludos, Francisco, los saludos también.
Me pidieron por favor que si nos podemos retomar una fila para si me podrían apoyar, por lo menos dejar esta fila para los speakers y los que van a estar en el panel para poder. Pues, no, creo que está bien. ¿Ah? No, está bien, nada más. Es que lo mejor sería que libre, porque no sé cuántas personas vienen. Ah, ok. Ahí creo que no hay bronca. Creo que me pidió que por lo menos en un lugar. Ya, más o menos. Sí, puedes estar así como... Sí, con esos están bien.
Unas horas. Por ejemplo, esta cosita que acabó de Es muy probable, pero poco porque hemos estado allá y tenemos más acá, lo más o sea, no es tan grave. Si tienes más pelos que no y no sé, la agarría también. Esto no es real.
that's why perdón de la confusión. He's always there. We know each other because the personality was on the same So I after many years, like we saw each other yesterday, and I said, you're looking at catching the big ideas. That's why we are here together. So it's Carlos, worried about the school
Bueno, hello. Good morning, everyone. So first of all, thank you very much, all of you, for coming here. We see that I have a huge auditorium and everyone is booked. So I'm going to be briefly giving out the schedule of what's going to happen today, and then we're going to go on to the conference. So let me see. Okay. So just for today, so in the morning, for those of us who didn't know, it was the summer school, the end of the summer school. We had 3 days of summer school with 17 total courses with 6 parallel tracks. And today in the morning was the conclusion. Now, today we're having 2 very important keynotes. So Joshua Benjo, who did a small talk yesterday, but today is going to be an actual keynote and talk to us a lot more in depth about everything about deep learning and all that he's doing. And then Jorge Nocedal, who mainly done optimization for machine learning and for many other stuff. As many of you know, optimization is one of the key workhorses of machine learning. So we're going to have a great talk there. After that, we're going to have a small break. And then we're going to go to the panel of AI in science and engineering, where we're going to talk about more applications of how AI goes into engineering and engineering applications. After another small break, we're going to have Alan Aspuru, who's going to talk to us about machine learning, including chemistry, and lots of other cool stuff that he was here last time, and he's going to talk again about what his current research is about. And in the end, don't leave, because there's going to be a cocktail and a poster session. Please go to the posters. There's lots of people who's going to be there, everything from students to professors to startups to companies. And a few other people who have won several either robotics conference and robotics events. They're going to be presenting their robots, their small robots, and people are going to be able to walk around, eat and drink. All right, so anyway. So now, just before starting, I'm going to briefly introduce Joshua Benjo, although probably there's no need, but I'll anyway go ahead. So Joshua Benjo is a professor at the Department of Computer Science and Operations Research at the University of Montreal and scientific director of the Montreal Institute of Learning Algorithms, MILA. He received his bachelor's degree in electrical engineering, his master's in computer science, and his PhD in computer science from McGill University. He was a postdoc then fellow at MIT. He has received many awards, probably some of the most notably, named an officer of the Order of Canada, nominated Fellow of the Royal Academy of the Royal Society of Canada, and received the Marie Victorian Quebec Prize. Finally, but not least, he won in 2018 the Turing Award for his work on deep learning, for which he is considered one of the fathers of AI, of modern AI and deep learning. Maybe many of you have read this book, but also something nice about it is that it's called Deep Learning Book, and it's freely accessible for everyone in the internet. Finally, but probably most importantly, he's a great advocate of using AI to mitigate climate change, to stop talk on AI arms race, and to make technology more accessible to developing countries such as Mexico and Latin America. So please, let's welcome him here.
Thank you for the kind words. These are the people at Mila. Today my presentation will be a bit more technical than yesterday. Feel free to actually ask questions in the middle if you want. I'll be happy to try to answer. Okay, so the core theme of this presentation is the agent learning perspective, usually called reinforcement learning, but I like to really make the focus here on the notion of actions and how that changes perspectives in terms of deep learning, which is the thing I care about, in particular learning representations. And one thing that really matters when you start thinking about the agent perspective, unlike the usual IID machine learning approach, is that we have to start thinking about the fact that when you act in the world, or there may be other agents acting in the world, the data that the learner is seeing is not following always the same distribution. It's non-stationary. So these changes in distribution become something important. And of course, I think they're also important in practical applications, but I think there's a lot of interesting fundamental issues that we have to revisit in learning theory and algorithms to handle properly this scenario. And one aspect that I particularly care about is how it becomes potentially easier, but also different, for an agent which observes its environments and can act in it to build an internal model of it, to really understand it in a way that's less superficial than what we currently have. Okay, so I showed this slide already yesterday, so just as a reminder that one of the aspects that I want to talk about today is how we extend the work that we've done in deep learning for learning representations from the system 1 tasks, where we can do good things at the level of perception, unconscious types of computations, into the conscious type, which is more algorithmic, including things like reasoning and planning, that is not just important in RL, but also when you want to do dialogues, for example, natural language understanding and things like this. Sorry. Okay, so here I have a little thought experiment, which I want to introduce in order to motivate the idea that it's not enough to do natural language understanding by training our learner on texts, which is right now what most researchers working on natural language do. We have these huge data sets, corpora of text and, say, translated text, or all kinds of NLP tasks where it's basically we would like the learner to understand what the text means, but we only feed it with texts, or sometimes with a few semantic or grammatical labels. But I don't think that's sufficient. And so here's a thought experiment to try to illustrate why I think so. Imagine you go to another planet and you observe the aliens there, maybe from your spaceship, that you can catch the bits that they're exchanging. And you'd like to understand what they mean, right? In a way, it's just a transposition of what we're doing when we do natural language understanding and language modeling and so on. But now the situation on this planet is going to be slightly different from on this planet. Like on Earth, there's going to be a price for bandwidth. So in other words, I don't want to send too many bits to my correspondent. But unlike on Earth, these aliens are able to send bits through a noise-free channel. Whereas, we use speech. We've evolved to use speech. And speech goes through a noisy channel. So there's a lot of redundancy in speech. And you can find that redundancy in natural languages as well if you just take the texts. So if you are one of these aliens and you have evolved a way to communicate efficiently, you want to take advantage of the fact that you can get you can get noise-free channel to optimize your use of bandwidth, and so you're going to compress your message before you send it. Right? So these aliens would compress their message. And you know what happens when you compress something? When you compress a file, you get really good compression, gives you random bits, right? Try to make sense of a zipped file by looking at the bits, right? It's very hard. So if we were to do like language modeling on the zipped files, right? Try it, you'll see it doesn't really work because it looks like they are random. So if we were to apply the techniques that we currently apply to analyze texts on this planet, it just wouldn't work. Okay, so what's missing? Well, unfortunately, the only way around on this planet, and I think on our planet as well, is we actually have to make extra effort to understand what those bits mean. And for that, we're going to have to understand the context of these speakers, these aliens. We have to look at what they're doing, trying to figure out their intentions, and build a model of their world, how it works, and what they do, and why they do it, and so on, which is going to be hard, much harder than just training a neural net on the bits that they're producing. All right? So I think we have to do the same thing here. In other words, if we want to do really good language understanding beyond just, incremental progress that will happen in the next few years, we have to solve AI, right? We have to build systems that understand their environment, understand our world. Okay, so one reason why I think we also have to do that is, I think something I mentioned yesterday, which is the current approaches, they'll get better, but they continue, even if we train them on huge quantities of data, more than any human has ever seen in their lifetime, they make sometimes really stupid mistakes, which reveal that they have learned lots of interesting patterns and some structure, which could be very useful in many applications, but they don't have enough of a deep understanding of how things work in the world. And so they remain vulnerable to changes in distribution. Whereas humans seem to be able to handle these things much more gracefully. But we need to understand how humans do it, and there may be a number of factors, some of which we don't yet understand. But one element that I'll be telling you about today is I think humans very quickly understand causal relationships. So 4-year-olds clearly understand causality, and it may start as early as 2-year-olds. There's a number of experiments that have been done to try to evaluate that. So, what's the thing with causality? As Pearl has been saying a lot, when you consider causality, you're bringing more information than what you get just in the joint distribution between random variables. And in fact, you can easily come up with cases where purely observing the joint distribution still doesn't tell you what variables is cause and what variables is effect, for example. So how could children figure it out if just observing the world is not sufficient? Well, it turns out that if you consider how the world changes, often because the agent or some other agent does something in it, you can acquire information about cause and effect. Like if I push something, I can see that it is my action that has created the change in the world, and maybe there's a chain of effects that I can observe and understand. And of course, if you're an agent, it's very important to know that. So I use this example of umbrellas and weather. Maybe it's not the best example, but rain can cause people to open their umbrella, but opening your umbrella doesn't cause the rain. The joint distribution is the joint distribution, and it looks like these things are very strongly correlated. But if you are an agent and you're trying to make rain happen, it's not going to work to open your umbrella. That's important to know for an agent. Right. So this is another topic that I'll talk about today, which is related to understanding how the world works. So there's causality, but there's another thing. The techniques that we currently have to model joint distributions, I don't think are a good reflection of how humans do it. So the way that I have the impression that I can project myself into the future to understand how my actions are going to result in some changes in the world does not involve something like running in my head a movie of all the things that could happen in the world at full resolution. Okay? That is not what humans do. Right now, our unsupervised learning methods and deep generative models allow us to do things like synthesize images of faces or images of houses or whatever. So it's all happening in the data space, in pixel space, typically. And this is great, and we can find lots of useful applications for this. But I don't think that's the way that humans use their imagination to project themselves into the future or try to find explanations about the past. Instead, I believe that the way we do it is we use more abstract representations, higher levels of representations, not the pixel level, and we learn how the world can change as a consequence of its dynamics or the effect of agents by modeling those changes in that higher level space. So one of the recent work we've been doing is using new techniques based on GANs to estimate mutual information in order to learn to map raw data into a latent space such that, for example, 2 consecutive frames in latent space would be highly informative of each other without having to do just maximum likelihood to predict one thing given the other in order to learn the encoder. Otherwise, there is a little problem, which is you can make the predictions very good in the latent space by making the encoder output constants, right? So if my abstract representation is just constants, it's very, very easy to predict the future in that space. So the objective function of just predicting things in the latent space is not good. But maximizing mutual information actually is a good replacement. So this is a thing we've been working on, and there are several papers around that theme. Let's see. Right. Now, in addition to doing all this projection about how the future could be in latent space, there's another aspect which I think is really important if we want to take inspiration from human cognition, which is what I want to do. And it's the fact that when I project myself into the future, as I said, I'm not seeing a full movie of unrolling the state of the world in the future, even the latent state. I'm only seeing a few aspects of the world which matter for my thoughts, for my planning. Right? So this is not something we've been doing in machine learning. Like typically, we think of it, say, as learning the probability of the future state or the future latent state given the past, or given the past and some actions. But that's maybe too difficult and doesn't feel like how humans do it. So what we need are tools to be able to produce a sequence of potential future events which focus on a few aspects of the world at a time. And I called this line of work the consciousness prior, because when we are conscious of something, I think it's this slide, we're focusing on our attention on a few aspects of the world. Right? We're not having in mind, at least consciously, the full state of the things that are available to our perception. We're just going for maybe a handful of things that we're concentrating on right now, and then maybe 1 second later it's a different set of things as our thoughts move forward. So this is use attention, and maybe we can use the progress we've made in attention mechanisms in the last few years to do something like this, to implement this particular aspect of consciousness that has to do with our ability to focus on a few things at a time in order to form a plan or something like this. So in this paper that I put out 2 years ago, which is like a proposal for exploring these ideas, what I have suggested is, instead of thinking of just one high level of representation, we're going to have two types of objects at this high level. We're going to have the regular state, which contains all of the information that we could potentially be conscious of. So all of the high-level variables would be represented there. And that's what I call the unconscious state H here. And we learn this encoder, which maybe is recurrent, that maps our perceptions to this representation that captures all of the high-level variables, potentially with their uncertainty, because usually there is missing information. And then on top of that, there's the conscious state, which is going to be a very, very small thing. Maybe a few, like what you have in short-term memory, right? So you know you can remember like 5, 6, 7 things at a time. So these are the things that you're currently conscious of or very close to, that have been brought from that large unconscious state into your consciousness. And at each time step, you're using attention to select what will go next. And you can use that conscious states to do things like projecting yourselves into the future for planning a path or a decision or avoiding problems, all kinds of things that we do consciously. All right, which basically are in the realm of reasoning, but the way humans do it is, I think, different from what classical AI with logic was doing it, because we don't explore so many branches, and it's also different from the kind of full state transition operator that we tend to look at in, for example, in model-based RL. So the paper was called Consciousness Prior because the way to think about this structure in probabilistic sense is that it's making a statement about the joint distribution between those high-level variables. So remember, I'm saying that we are mapping the observations, which may be a stream of observations, into this very high-dimensional unconscious state. And what I'm now claiming is we're using this conscious stuff to capture the joint distribution between all of these variables through very small nuggets of knowledge, which you can think of rules, if you think in classical AI and so on. Or you can think in terms of graphical models as the joint distribution between all these high-level variables is a product of potential functions. So these are functions of a few variables at a time. So each of these functions, this is a scalar, and this VSK here means we have a small clique, a small group of variables which interact together to contribute to the potential, to the total probability function. Right? So there's already a lot of work in graphical models that uses this kind of formalism, which is called a factor graph. And the particular way to think about the consciousness as a prior is simply to say that the corresponding joint distribution is a very sparse factor graph. In other words, these potential functions, these strong dependencies between variables are involving very few variables at a time. Basically just enough that can fit into your consciousness bottleneck. And I think there's something to this assumption which we can all experience. When I make a statement like, if I drop the ball, it will fall on the ground, it's just a few words. It talks only about a few concepts. And you can think of, maybe there's like a potential function which we can instantiate to express this knowledge. And what's particular about it, in addition to the fact that it involves very few variables, is that it can make very strong statements from a probabilistic perspective. In other words, this sentence is true with very high probability, right? And this is unusual. Like, you don't get this usually. If I were to make statements about pixels at the level of pixels, I would be very hard pressed to come up with a statement that I could make that involves only 5 pixels and could make a probability guess about one of them given the other 4, where the probability would be very certain, like either close to 0 or close to 1. Right? So these are strong probabilistic statements. They're like constraints. They're like rules. Right? So that's the idea of the conscious prior, and it's called a prior because we're going to assume a structure like this, and we're going to encourage solutions that have this sparsity. And what I believe is it's going to help us learn more appropriate high-level representations. Because where we started from is we want to discover from the world the right variables, and not all variables have this property that their joint distribution can be expressed as a sparse factor graph. So by imposing that prior, we're encouraging our solutions to have this this assumption built in. Yeah. Let's see, how am I doing with time? So the introduction of action that I started talking about and causality is also connected to another notion that people in RL have been thinking about, which is the notion of controllability. And I think we can use these notions to help us also put more pressure on these high-level variables. So a lot of the high-level variables that we communicate with language, like names of things and attributes of things, like say, I have a concept for this pointer, and I also have a concept for the position of this pointer. And these are non-trivial functions of the pixels, right? That somehow my brain is computing. And there's something interesting about many of these variables is that I can control those variables. I can change them. I can come up with a policy, with a sequence of actions, which can selectively perturb the position of this object. And, well, more generally, there are agents in the world that can do these things. And if no agent can do it, we usually imagine that an agent can do it. Like, people used to think that the sun was like a living being that could move itself, right? Because it fits the prior that the things that change are changed because an agent is controlling them. So this is another thing we can use because we can now say the variables that we want to put in there should have a high mutual information with the policies that an agent can build that have as an effect to change those variables. There's like ideally a one-to-one mapping between policies, like what I choose to do, my intentions, and the effects that I have in the world. If I had a pure one-to-one mapping, I would have a total control on everything in the world, right? And so it's both a way, this connection is both a way to learn good representations of the state of the world and to learn good policies, because we want policies that can allow us to do anything we want, right? So this is, I think, an important concept moving forward. And we started working on this a couple of years ago, and there are several papers along that line of work. All right, so let me go back to this issue of changes in distribution. As you probably know, the classical learning theory you would learn if you were to take a machine learning class 101 is one which assumes that all the examples are coming to the learner independently and from the same distribution. And we have a lot of nice theory that when you are in this setting tells us that you will be able to generalize it, so long as your learner is not too powerful, right? And that's great. But in the real world, this assumption of IID data does not hold. The world keeps changing. So how do we deal with that? I don't think we have the right tools yet in machine learning, although there is some work, for example, in causality. and in meta-learning and transfer learning, people are starting to think about these questions. But there's a lot more that needs to be done. Right. So connected to this, the way that I'm thinking about it is, well, if I want to be able to say something about generalization to a different distribution, I'm going to have to make assumptions about it, right? Otherwise, well, what can I say? I mean, if I suddenly wake up in a totally different world where nothing that I know continues to be true, then, well, it's not going to be very good for me. I won't be able to act in the world and be successful. Right, so what could we assume that's reasonable about those changes in distribution? And what I'm claiming is that in the world of agents, we could assume that the changes correspond to small changes that are localized. So when I move this pointer, I'm making a small change in the world that's very, very localized. And it's localized in space and in time because, you know, I'm physically in this one place in this one time, and it's hard for me to change everything in the world from, you know, just my thoughts. But I can change my, you know, my arms around, move my arms around, move some things around, and so on. And it's true for many agents. So it's a good approximation of what kinds of changes are happening in the world in terms of the distribution of things. And it's connected to an idea that has really impressed me a lot, that I read in the book of Peters, Jensing, and Shopkoff about causality. The idea of independent mechanisms, which essentially says that the world we observe is the result of the combination of independent mechanisms. So light goes through different media and then it comes back to me, and each of these intermediate steps you can think of computations, but those computations are independent of each other. What does it mean that they're independent? Not in a statistical sense, in the usual sense, but in the sense that knowing about, say, one of these mechanisms doesn't teach you about another one. And that, you know, if one of them changes, then the others don't need to change, so they're not linked by some hidden secret thing. Under the right model of the world, right, like the laws of physics, the way that physicists understand the world, this is very reasonable. And so combining these two things, I think we have a path towards doing a better job at understanding how we can generalize in a world that changes under these kinds of assumptions. So, so the idea is, if I represent my knowledge about the world as a composition of little pieces of knowledge, like the rules I was talking about before, in the right space, if I choose the right representation that corresponds to these independent mechanisms and corresponds to this assumption of small local changes when there is an intervention, I'm going to be very lucky because the change is going to be localized and going to affect only a few variables or a few parameters that would need to be inferred or adapted to take into account that change. So that's actually connected to another problem with deep learning and maybe machine learning often, but especially deep learning, which is the problem of what's called systematic generalization. It also has to do with generalization outside of the training distribution, and it has to do with how the knowledge we've acquired through learning can be recombined in new ways that have never been seen in the training data, and that has zero probability under the training data, and that we could still generalize to these new ways. And humans do that all the time. And especially when they reason, when they use system 2, they do that all the time. And current neural nets usually fail, and there's several papers from my colleagues like Aaron Corville. I've been looking at the failures of current approaches. I mean, it's not a total failure, but really there's a big drop in performance when you do these kinds of changes. Okay, so maybe if we can entice a learner to find the right representation of knowledge into small reusable pieces, we'll also be in a good position to deal with these changes in distribution if our assumptions are good. So this is what we've started to do. And as an illustration of this, we've studied a really, really simple system, the simplest possible system you could imagine, one in which you only have two random variables, A and B, and you're trying to learn the joint distribution of A and B, right? This looks like a really, really toy, but trust me, science often starts by really, really simple problems that we try to understand fully. And even that is not so easy to completely understand. So if you're trying to represent that joint distribution, you can do it in many ways. In particular, you can factor the joint into the product of one marginal and the appropriate conditional, or the other way around. But if you have the wrong factorization, so you can think of, now my modules are the marginal of B and the conditional of A given B. But maybe the right way to divide the joint is the other way around, in the sense that A is the cause and B is the effect. In that case, you would like to use the other factorization. So why is that? Because if somebody comes and changes the cause A, it's going to change the marginal P of A, but it's not going to change P of B given A. So why is that interesting? Because if I'm going to have to adapt to that change, to recover from that change, and I only have to modify a few parameters, like those that control the marginal of A, and I don't have to modify all the other parameters, like P of B given A, then I'm in good business. Like, I can learn quickly from very few examples. Whereas if I have the wrong modularization, the change in P of A here would percolate into both this marginal P of B and this conditional P of A given B, and so I would have to adapt all of my modules. So if you have the wrong modularization, which I think is what we have right now with typical neural nets, where there's often no modularization or not one that is learned appropriately, when there's a change in distribution because of continual learning, transfer learning, or whatever, all the parameters want to be part of the change to adapt, and that means you need a lot of data to adapt to that change. So you get things like poor transfer, catastrophic forgetting, and all that. Yeah, let me skip this. So we're gonna go back to this picture, and now think about it in terms of what I was saying, that, well, if we had the right decomposition and the right factorization and so on, and the right set of variables, then we would get fast adaptation to interventions. Can we turn this around into an objective function that tells us how to optimize our choice of variables, our choice of graph? That's what we've tried to do. Whoops. So I think we're missing some colors, but anyway, it doesn't matter. So this is one part of a set of experiments where we try to validate these ideas. So this graph only shows that if you had the right factorization, then the likelihood would grow up quickly when you move to a new distribution. If you have the wrong factorization, it takes a lot more time. Eventually, asymptotically, the two will converge to the same thing. But so what matters here is the signal about the advantage of having the right representations and so on will be seen early on when the system is struggling to adapt. This is where there's most information. So in other words, where it's hard to generalize is, well, there's the most information about what is the right way of decomposing your knowledge. So we wrote this paper, a meta-transfer objective for learning to disentangle causal mechanisms, to explore these ideas. And we're able to show that practically it works on these very simple distributions. And we have another one where we extend this to larger sets of variables. Now, there's an issue here, which is the objective function that I've defined here is how fast you adapt to a change in distribution. That's like a weird objective function, right? It's not the usual like maximum likelihood or things like this. And it fits into the more general scenario of meta-learning. So what is meta-learning? Meta-learning is basically that we have two levels of learning, right? Learning to learn. I wrote a paper in 91 about learning to learn a synaptic rule. And when you have two levels of learning, where there's an inner learning loop and an outer learning loop, where the outer learning loop needs to take into account what happens in the inner learning loop. So ideally, you'd like to backprop through what's going on in the inner learning loop to get a gradient on how to change the parameters that control the outer learning loop. So we already do that when we do hyperparameter selection, right? So when you choose the size of your model and learning rates and filter sizes and all these things, you're choosing the outer loop parameters. So there's like, you try many different choices of these parameters. It's learning. It's usually done in a very dumb way, but it's really learning. But nowadays we can do more powerful things where the outer loop is not just a few parameters, but might be like a whole encoder or a whole neural net. Yeah, so that's the idea. You can formalize it in terms of like inner approximate minimization and then an outer one, which uses the result of the inner one as, you know, some of its arguments. And that's basically what meta-learning is. And so what's cool about it is that you can use meta-learning for many interesting things. In particular, you can use meta-learning for learning how to generalize better. That's how we use hyperparameters, right? We check how well they work on the validation set, right? So actually, we're optimizing for generalization. But we can do even better than optimizing for generalization. We can optimize for transfer, right? So we can optimize for how fast we learn on a new distribution. This is something cool because it gives us a tool to deal with this problem of changes in distribution that I was telling you about, right? So I said learning theory doesn't give us any guarantees that when the distribution changes, we're going to generalize. But what if we train our system so that when the distribution changes, it performs well, it learns quickly, right? That's what meta-learning allows us to do. So this outer loop is a way to now do learning theory on a different plane, which is one where each example at the outer loop level is not like an image, but each example is a whole inner loop, is a whole like scenario, like a trajectory in RL, or a sequence of 5 examples of a new distribution. So we call those meta examples. And often we think of these meta examples as coming from a distribution over distributions, right? So we're going to have many tasks, for example, and we have a distribution over tasks. All right. So I think I'm going to stop here. Maybe say a few words about how I see this moving forward, and summarize a bit of the things that I've been saying. So some of the things we're trying to do in my group is train agents that can interact with their environment, build a world model which captures causal effects so that they can quickly adapt to changes in the world, and generalize out of distribution. And one thing I didn't talk a lot about, but I mentioned controllability, is connected to how the learner can actively decide where to go in order to acquire more information. So that's exploration, but it's not like random exploration, like is typically the case in RL, but something that's more directed towards acquiring knowledge. And finally, I think that making progress on these things, learning the right variables at the high level, is starting to give us the tools to think about how neural nets can do planning of a form that is different from the things that happened in the past, but I think will be necessary to bridge the gap to a human-level AI. I have a few more slides, and it's a different subject. So, as a researcher in this field, I feel like I can't just do my research without ignoring the fact that the work we're doing is having an impact in the world and will have even more of an impact in the future. And so I think it makes sense for us who are building this future to talk to people who are working in society, who are academics or politicians or media, and the public, to discuss together what are the things that are acceptable on how AI is going to be used, and what are the things that are not acceptable. Some of the things that I'm concerned about include how machine learning could be used to control population, so the big brother scenario, because we can have cameras all over the place that watch you. It includes things like lethal autonomous weapons, killer robots, that can really threaten the security of people in many countries, and could also be used to control populations. There are lots of issues, I think, that governments will have to think about, and many years in advance, about how those technologies might change a job market in a way that could create a lot of misery. So think about all the work that is being done in factories right now by low-skilled people and might be replaced by robots in 10 years from now. How do we deal with that socially, right? Where are we going to get the wealth to make sure that we can avoid the misery that may, at least in the transition, happen because of all these changes? Another important topic, I think, in the last couple of years has been more obvious, is how machine learning is being used and will be used even more in the future to manipulate people. And the first place where this is happening is advertising and social media, as we've seen in political campaigns, where political advertising can take advantage of machine learning to have an undue influence on democracy and endangering democracy. There was discussion already yesterday about social biases and discrimination, I think another important topic. And there's a more general fear that if we don't collectively change to some extent the rules of the game, we might go into a world with even more inequality between people, between countries, and between companies. Because AI can become very, very powerful. And of course, if you have power, then you tend to use it to acquire even more power. And that's not good. That's not good for democracy. That's not good for most people feeling good about themselves. Yeah, so I guess I'm going to stop here. Thanks. So I took a bit more time because Jorge said you can eat in my time up to 20 minutes. And now we have time for questions.
Yeah, we have enough time for questions. So can people raise their hands? There's people there with microphones.
Thank you very much for your talk. And my question is about the use of the term consciousness in your talk.
Yes.
Because it seems to me that your distinction is much closer to the old traditional AI divide between the sub-symbolic and the symbolic. So in a sense, what I thought, I have understood, is that your concern is really to bring the sub-symbolic into the symbolic in order that things are more transparent somehow, with all the benefits that it has. But my question is really, in the old distinction between whether machines can actually be conscious, and I'm thinking of Searle's papers on the Chinese room, and the possibility that machines really understand and really be conscious and really be intentional and all that.
Yeah.
So, are you implying that somehow you reach that level of consciousness, you and consciousness, or you just use consciousness as a kind of synonymous of declarative or symbolic level? And well,
all right.
And also the other would be
let you do one thing at a time.
Right. Okay.
So thanks for asking the questions about consciousness, because it's high time that scientists start to study this question in the scientific way and try to dissect this into things that we can understand computationally. And there are different aspects to the word. The word consciousness is used in many senses. And so we have to, first of all, clarify what these senses are. And in this talk, I was only talking about one aspect, which is sort of the attentive consciousness, right? There are other meanings of the word consciousness. When you referred to Searle's, there is the notion of self-consciousness, I think, which is fairly easy if you have an agent in the world, that it has to know about itself and its role in the environment and its goals and things like this. And then there is the qualia, which is maybe related to Searle's or maybe not, which has to do with the subjective perception, which I think is a non-issue, because when you use things like deep learning, where you learn the internal representations, Of course, each agent is going to have their own perception, their own representation. None of us has exactly the same representations. And so we will interpret the color red in different ways, and it may be associated with our good or bad experiences in the past. Now, for Seoul's Chinese room, I don't buy his argument at all, right? I mean, according to his argument, essentially, you wouldn't be conscious either, because what is your brain? It's just a collection of little agents, neurons, which interact with each other, and each following a simple set of rules. Yes, it is.
Well, just follow up, just close it down. So you think, I mean, that the distinction between experience and consciousness is not an issue, right? But I mean, if you put it in more terms, I mean, the strong problem consciousness, I mean, you mean also that it's not an issue as well?
That's right. I think we can eventually in the future build conscious machines. Absolutely. Now, whether we want to do it is another question.
Yes, a pleasure. Thank you very much. I'm Leobardo Morales from IBM. And in a conference of the next equation of AI, you mentioned the human is very good in unsupervised learning, no?
Yes, that's right.
How do you can explain with a little example how we can advance in that way with the machines?
Right. So in fact, a lot of my talk was about this, because it was about learning good representations that capture how the world works, which is, I think, really what unsupervised learning should be about. And in addition, the classical unsupervised learning was only focusing on capturing the joint distribution, and I've been saying unsupervised learning need also to encompass capturing causal relationships. So yeah, we have a lot of work to do, and maybe it's going to take many decades before we solve these problems. We have to be patient. This is what basic research is about.
Hey.
Yes.
So I was wondering about this idea of this higher level representation
Right.
that you call the consciousness. And in terms of if you are thinking of like changing representation when you go to higher levels. So maybe if you go to a higher level, you go more to a logical representation, and then you do other types of reasoning.
Yeah.
And I imagine that's what we do, but what do you think?
Well, so I don't think that human brains are very good at logic. So we do a little bit of it. We're able to do like a few steps of logic. And so we have mechanisms that allow us to do things that are logic-like, but are weaker in some way, but also more powerful in other ways. So where it's more powerful is that our reasoning steps can be anchored in a very, very rich understanding of how the underlying world works, right? So that's what common sense knowledge is about. Like, I can say a few words in a sentence, and it's not just the logic here that relates those things. There's also underlying understanding of rich relationships between the things in the world that may be relevant to really interpret that sentence. So yeah, human reasoning, I think, has some flavors of logical reasoning, but it's also different because of its grounding in system one.
What kind of policies could reduce the gap between countries, companies, and people related with machine learning?
Right. It's not just related to machine learning, I think.
Okay.
Yeah.
Are-
So,
AI.
so you're asking for like, basically, how do we get to world government, right? I mean, that's like the natural place we'll eventually have to go, to some form of global coordination. We're trying to do it already step by step by having international agreements and things like this. But organizations like the UN currently don't have enough teeth. They don't have enough power. And so we don't manage to solve problems because right now it requires essentially consensus, like or at least consensus of all the rich countries. And so that's not going to work. That's one of the reasons why fighting climate change is not working right now at the international level. And it's one of the reasons why the problem with lethal autonomous weapons is not progressing, because it's enough that one country, like the US, for example, says, I don't want to sign a treaty like this. and nothing moves. So we need a more powerful global order, which still respects, local issues and sovereignty, but there's I think the general principle should be everything that can be, all the decisions that influence mostly what's going on locally should be taken locally, and all the decisions that influence what's going on elsewhere have to be taken at a high level. Right? And there are so many things right now, like the environment, and handling like inequity between countries and all these things, which can only be handled at the level of the whole planet. So then how do we get there? Well, so I have an idea. The idea is to create a club, right? So in a way the UN was, well, not the UN, the EU was moving in the right direction. Now I'm not sure anymore. So let's say you had a club of countries which say, we're going to link together our commercial, like free trade agreements with our political agreements about things like how do we handle environment and fiscal and all these things that need to be agreed upon in order otherwise we get into a tragedy of the commons. So there might be an initial group of countries which agree with something like this and basically tell the other countries, if you want to be part of our club, you have to accept the rules of the club, and you can then, as a member of it, you will be voting for the same things in a democratic way. And if you're not part of the club, then in the next 10 years, we're going to be gradually increasing tariffs, so you won't be able to make business with us at some point. So in this way, you create a sort of a game in which the incentive of other countries is to just join the club.
Okay, so I also always include in my talks a slide about Big Brother.
Yes.
But when people ask me, so what to do? I don't know what to say. You have a slide?
You have to first have people realize that it's an issue. That's the first step.
Yes. But you have a slide about research that we should not do.
That's right.
The bad thing is that the bad guys will do it and you will not. And then we will be just in disadvantage because they will do it secretly.
Yeah, it's exactly the same issue that I was talking about 5 minutes ago in for the last question. That the only way around these tragedy of the commons issues is to agree on collective rules, right? That's why we have governments, right? So if we say, well, we make a treaty that just like we have been banning chemical weapons, we can ban lethal autonomous weapons, right? That's the only solution.
Looks like artificial intelligence is much more difficult to control than nuclear development or chemical weapons. Bad guys can do it secretly without the governments noticing it. If we, governments and good countries, will not have this technology, but they will have it.
Well, it's not so clear. So you're right. So there could be terrorists or rogue organizations which secretly do bad things. But if, so the rest can also be acting defensively and preventively, right? So we can use AI, for example, to design weapons to kill killer robots. But the most important thing is to create an international consensus in the populations that some of these behaviors are immoral and are not acceptable. And then most people won't be willing to do this kind of work. At least that's one hope. I mean, do you have a better solution?
Hi, my name is Yana Avila from ITAM. Thanks for your talk. My question relates to people like AI communities, scientists, researchers.
Yeah.
What are the specific responsibilities they should assume, the specific actions they should do in order to make sure that AI is going to be used for social good and avoid the concerns you were talking about?
Right. So I would say the first thing is to get educated about these questions. So for example, I think that all students in computer science should have mandatory course in ethics. In fact, similar to what engineers have to do, but more oriented towards how AI and computer science could be misused. So that's the first thing, like understand the issues and understand the citizen point of view so that you can then start thinking and reasoning about, well, what is it am I doing? How is it going to be used? What might be the impact, right? So that's the first thing. And then that's the individual level. And then we need organizations who are going to be watchdogs. We need governments. We need civil society to try to monitor what is going on and potentially create rules, that social norms, to minimize the misuse of technology. Yeah, that's it. Very easy.
Thank you.
All right. Thank you very much, everyone. Let's thank again, once again. All right. So now moving on to our second keynote of the day is going to be Jorge Nocedal. So as many of you might know, optimization is one of the key factors that's made machine learning successful. And so Jorge Nocedal was born and raised in Mexico. He obtained his bachelor's in physics here at the National University of Mexico. He then pursued a PhD in mathematics at Rice University. He has won numerous awards in the fields of nonlinear optimization, applied mathematics, and operations research. He was named an ICES highly cited researcher in 2004. He received the George Dantzig Prize in 2012, the Charles Broyden Prize in 2009, and he was also named Siam Fellow in 2010, and in 2017 he received the IFORM's von Neumann Theory Prize, amongst many others. He is well known for his research in nonlinear optimization, and is notably the inventor of the LBFGS method, a limited method of a variant popular quasi-Newton method, FGS. Many people here might know him from his book Numerical Optimization, which is the most highly cited work on continuous optimization, and it's actually one of my favorite books, so very recommended. So please give an applause to Jorge Nocedal.
I forgot there was a microphone. Thank you to all the young people who are organizing this event. It's full of energy, it's full of enthusiasm. This is what we need. Something that I think you didn't mention, thanks for the introduction, is that after I got my PhD, I came back here to teach. So I was teaching at IMAS, just across the street. I was there for 3 years, doing, PDEs, optimization, and so on. And at that time, enthusiasm was as big as it is now for other fields, right? So it's a pleasure to meet all the Mexicans and everybody else who's here. And I'll talk a little bit about optimization. So we're going to go back from high-level societal problems to the structures, questions about structures of neural networks, and so on. I will just make one comment about the question about how can we reduce inequality between countries. Because I'm a very simplistic person, my answer is just 2 words. But I think it's something that has been lacking here and lacks in the Hispanic community in the US, and that thing is value education. And I have not seen sufficient improvement in that. And it's so notable when you meet Chinese students and how society values education and how it pushes it. We have to do more about this. This is my very simplistic way of how one particular type of people can move forward, right? All right, value education, it's a lot of fun. In addition to being economically. Now, I'm going to give a talk about optimization geared to reinforcement learning, derivative-free optimization. But before that, given the discussions that I had yesterday, I thought of putting a few controversial statements on the board so that Joshua can get other technical questions. Or all of you can think a little about this, right? So the first statement is, it seems to me that people who develop neural networks got really lucky. Now, why did they get very, very lucky? Well, they were thinking about certain functions, certain structures that would be good at creating representations. And then this idea came that they call backpropagation, which really meant it is possible actually to optimize the parameters of such a complicated network by means of a gradient-like method, right? This is a common situation in scientific computing. Once you have gradients, you get the possibility of solving really large problems. Without them, you cannot. That's going to be the second part of my talk. So why did they get really lucky? Because I don't think it was clear, and maybe it's still not clear, why the minimization of that problem, the optimization of those parameters, which is a non-convex, non-linear problem, can actually be solved. So, it could be the case that every time you change the data, you get a different solution. And just to emphasize this, all my career has been about non-linear, non-convex optimization. And it's been really fun, because the Russian school of optimization, Nemirovsky, Nesterov, they were studying convex optimization. And for them, the world is, there is a solution to the problem. And you can find out what the speed of the algorithm is going to be in complexity analysis, and everything is very beautiful. What happens if a function is non-convex? Then where are you going to end up to? Why are people doing non-linear, non-convex optimization? Where are they doing it? And the truth is they're doing it all over the place. People are designing airplanes, chemical refineries, everywhere, designing glasses and so on. But how can you possibly do that? Well, if you have some progressive glasses there, we can optimize them, starting with the design that you have. And we hope that, we're going in a basin of a minimizer where it makes sense. So airplane design, this is done all the time, right? You have a fluid flow, and you want to make sure that the shape of the airplane is such that you minimize drag. You have certain properties, right? How could you possibly solve these are nonlinear fluid equations? Well, you start with a very good starting point, and you end up there. And the joke I always used to make in class when I was teaching is you do not design an airplane by taking a block like this and then saying, I want optimal aerodynamics, let the optimization do all the work. It won't happen, right? But here, the optimization is doing a lot of the work, right? So they got lucky, I think, right? So just to emphasize this a little bit more, you know that Minsky and Papert wrote a paper criticizing the perceptron, and they keep writing about this. If you go to the 1961 paper, he says, I doubt that any simple mechanism like hill climbing, gradient methods, will find the means to build an efficient and general purpose machine. Okay, fine. Then they went on in 98, in their second book, they're still saying, if we can detect relative improvement, derivatives, then hill climbing may be feasible, but it requires some structural knowledge of the search space. Unless the structure meets certain conditions, hill climbing may do more harm than good. Okay, people will say, well, they were wrong, right? But what they were bringing up was very real. There was some structure. It was possible for hill climbing to do all of this. And not only deal with non-convexity and non-linearity, but with a high dimensionality. Optimize a nonlinear function, which is non-convex, in 1 million variables. There's an extremely difficult problem, right? But what happens? Well, the practitioners found out that if they run the stochastic gradient method with some initializations and some tricks, it tends to get to the same solutions. And I remember asking Jan LeCun for many years, do you get the same parameters? No, I don't get the same parameters, but I get the same solutions. I get the same predictors. You're getting that. Well, you're lucky. How, in this space of so many minimizers, we do. Now, there's a lot of work. Now, for the mathematicians, there are papers coming all the time. What can I explain about these functions? Are compositions, right? Compositions of linear functions and piecewise linear functions. What can I say about them? So there's a stack of papers saying, for one layer neural network. And there's some other interesting work that say overcapacitating makes the optimization easier. And this is a general principle in applied mathematics that lifting the space makes things possible. In differential equations, often it makes things stable, right? Okay, so optimization is working. Let's hope that it keeps working. But a valid question, this is backwards, right? The one that goes forward is the one that goes backward? Yeah, okay, this one. Now suppose that someone figures out how to solve partial differential equations using neural networks. Well, that particular function that you're going to find out is probably very different from the function you're using for doing image classification. How do we know that you can actually optimize that function? Well, hopefully, probably because neural networks have been working in a number of domains, but there is no guarantee. So that continues to be an issue of this kind. And the other thing that I was going to mention here that was not part of my slides is there's a lot of interest in saying, in thinking about where can I take machine learning into other domains? Can I substitute laws, physical laws, by a neural network? Or can I combine them? And one of the most popular topics is called physics-inspired neural networks. There's a lot of people working on physics-inspired neural networks. What does that mean? Well, I don't know, but what has been done? And I want to mention one work that has been done because you hear about a lot of people having success in material science and so on. A lot of that is imaging. They're taking results that we know work, taking imaging, and clearly that works, right? So there is a work, Professor Brown Janikati, a name like that. He's solving partial differential equations with neural networks, or so he says, right? And so the idea is a neural network is just it's a function. And the set of parameters that you choose form a variety of functions. So it's a basis for a space, and that basis may contain the solution, the actual solution of that differential equation, right? And so physics-inspired would mean maybe that in the neural network architecture, you're putting knowledge that you know about that domain, right? But that's not what they do. What they do is they have the PDE, they have initial conditions, they run the neural network to try to make the prediction, and compare it with the result that the PDE would have given you. So the PDE is a residual, and you do least squares. And then you find out, optimize the parameters so that it gives you the same properties as the PDE would give you, right? So in this sense, it's not physics inspired or physics based, but it's physics constrained neural networks. Maybe it's interesting, probably will be quite limited. There are papers like that. I would not recommend to reading them now because it takes you a long time to find out where the difficulties are being circumvented. But that's interesting. That's really promising. The set of functions that can do powerful things. So finally, what are neural networks? In its simplest form, a linear function, then a ReLU function, piecewise linear function, and then a composition of this over and over. Now, another basis is just the basis of polynomials. But this particular basis has proven to be very useful. It is known that that is the case, right? So we have a function. They can create certain sets of functions. Let's imagine that it's a variety like this. And you have a certain task. And you want to find within this possibility that neural networks can give you the one that is going to be able to do that task. So it's a projection. You want to find, over here, the best function that gives you that. And that's a nonlinear projection. In general, projection is nice. Linear projection, boom, there goes on the board. If the constraint is nonlinear, the projection requires iterations. And how do you do multiple projections? By means of optimization. So the optimization algorithm is trying to find within this variety the function that does the best job. But nobody knows that this is done to optimality. So it turns out that doing some sort of optimization helps. And I don't know if anybody has any complaints about what I said. Okay. I was expecting. So this is the real talk. Derivative-free optimization, zero-order optimization methods with applications to reinforcement learning. My student Albert Barajas did a lot of this work here. Some of you know him. It's been published. Somewhat I wrote here has been published in SciOp recently, and the work on reinforcement learning, we're doing that now. So suppose we want to minimize a nonlinear function using only function information. You do not have derivative information anymore. Now you're really handicapped. And now suppose that in addition to that, every time you evaluate the function, you get noise. You don't get the right function value. Question. Is there today an optimization algorithm that can solve this problem with the number of variables is in the thousands? And to my knowledge, the answer is no. And such an algorithm would be needed in reinforcement learning. Such an algorithm does not exist now, and I'm going to propose one that works in the thousands of variables, not in the millions of variables. So where are applications where we want to solve an optimization problem using only function values when in reinforcement learning would be a case? And there are many scientific applications where this occurs. All right, so if you want, let's get, and see the problem precisely. I want to minimize a function. So I use my hands a lot, right? It's a non-convex function just by you telling me function values. Function is phi. I'm going to assume that it's smooth. Now, neural network with ReLU functions is sort of smooth. Well, it's smooth, and I'm going to have errors every time I evaluate the function. I'm going to try to get a gradient. Without a gradient, I don't know where to go. So we're going to get an estimate of the gradient, but it's going to have some noise. So the true problem is to minimize the objective function phi while only observing the noisy function f. In contrast, in neural networks, where everything was so beautiful, we don't need derivative-free optimization. Everything works out sort of perfectly in that environment. You have your empirical risk, the composition of the prediction and the loss function, and you can decide to make a simple, inexpensive approximation of your objective function, right? So you have this complicated objective function, make a simple approximation to that, and get the exact gradient of that approximation and move. And they used to call it, let's nudge the variables a little bit. That's normally not the way you do optimization. Say, if someone is doing a fluid flow simulation or materials, you don't just give it a few data points, integrate the model, and with that make a change. You have to give it a lot of information so that what you get is meaningful. Just think about the weather forecast. So if I just have a new example, it is not going to work, right? But here, it works that way. So you're nudging the optimization in this way with the stochastic gradient method, and you have the exact gradients, and things become very high scale and they work. So that's very nice, but this benign representation will not exist, for instance, in reinforcement learning, where things are a little bit more messy. The reward functions, the action models, so on, may even be discontinuous. Right? We may not know them well, they may be black boxes. And so there are two main approaches that people have been using in reinforcement learning. In reinforcement learning that uses neural network policies, right? One is the policy gradient algorithm. Here's a formula, a well-known formula, by which you can compute the gradient of that function by doing some expectation. You have to do some sampling in order to do that. And the other way is to do derivative-free optimization. Try to do reinforcement learning without computing the derivatives of the problem. Okay, so how do you do derivative-free optimization? Let's think about the simplest black box. So some chemist has got a really nice simulation. There are some parameters, and you want to get it really right. All you see is you tune, and you get the result. You're not allowed to see anything inside. How would you do it? How would you do optimization of that function if it's nonlinear, it's noisy? Well, if you go to our friends, the Russians, the complexity school said, well, in the worst case, the best thing you can do is sample at random. Sample a lot, find the function, smallest function value and move there. That algorithm from the point of view of complexity is very good. From a point of view of computation is really bad. So you can just keep sampling, and every best function value you move there. Clearly, you should be able to construct something better. If you evaluate the function many times, you construct a model and use that model to tell you where to move, right? And so really, the key here is not to be blind. If you have observed the functions in various ways, you can do a gradient approximation. With a gradient approximation, we can go. And the key about this talk is to do gradient approximations of noisy functions. This is not simple. All right, so I'm going to get there in a moment. All right, so in terms of complexity, sample everywhere. But now, if I have evaluated the function at many points, isn't it natural to save those function values, create a quadratic model of that object function, and then say, well, I'm going to move to the minimum of this quadratic model subject to a trust region. I'm not going to make wild steps because suppose that the model is concave. I put a trust region and I move that way. So I need to construct a quadratic model based on function values. This is pretty simple. How much information is there in this matrix here? N squared pieces of information. And here is about n for the gradient. So you're going to need about n squared, n is the dimension of the problem, n squared function evaluations in order to construct a quadratic model that will work well. And remember, our intuition in 2 dimensions really fools us completely. In 2 dimensions, you say, pom, 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 I create a quadratic model. But if I have 100 variables, it becomes really difficult. So it's n squared. This can be done and has been the state of the art in derivative-free optimization for many years. Not simulated annealing, not genetic algorithms, not pattern search methods. This has been the state of the art, creating those models. There's sophistication in them in order to reduce the computational cost. It turns out that every iteration costs d to the 4th power, the dimension of the problem, the 4th power, in order to decide how to move. Now, the 2 main people, I think, who have promoted this area are Mike Powell, the late Mike Powell, the great figure of optimization, and Katja Scheinberg, who's now at Cornell. These 2 people really have led this field for about 10 years. This has been the state of the art. And I really like them. These are really great people. Therefore, I'm going to now attack them. Therefore, I'm now going to say that what they were doing is not really the right thing to do. It was an overkill. They were interpolating function values. And function values is not as good as interpolating gradient values. It's going to be better to create noisy approximations of gradients and do interpolations that way. Okay. How do we compute the gradient of a noisy function? What does it even mean, the gradient of a noisy function? So what's the noisy function? The true function is the dotted line. And I've added there some noise. This is not realistic noise, I've added that. The only thing I observe is the red function, is the red curve, right? How am I going to compute the derivative of the real function using that noisy function there? Is this possible? Is this impossible? Well, there are two ideas that came out at the same time in the last 5 years. One of them is, if you have a function that is noisy, just sample around that function and average. You smooth the function. Okay, it's a natural thing. Even in n dimensions, you get scared about sampling in a ball, but there's no free lunch. If you really want to optimize a function in 100 variables, there's so many ways to go wrong. So you have to make an effort to get the gradient, right? So one idea is to smooth the function and compute the gradient of that smoothed function. Nesterov actually wrote some theory about this. The algorithm then is very simple. You're at a point, evaluate the function many times, and then compute the gradient of that smoothed function. And the gradient is given actually by that formula that looks like a finite difference. The only difference with a finite difference is this. You take a random direction, tiny step, evaluate the function there, and compare it with the current function value, and multiply it by the random direction that you have. And repeat this a number of times, and that's going to give you, the more work you put, a better approximation to the derivative of that smoothed function. This is called Gaussian smoothing. This is the algorithm. A lot of people are using that in reinforcement learning. It lends itself to that setting fairly well. Now, what we have done is something different. What we have done is said, to evaluate the function in random directions may not be needed. Maybe classical finite difference approximation to the gradients will work if you only know what the finite differencing parameter should be. For a noisy function, we can do that. So I make a claim, and I'll show in a moment, that there is, for any noisy function, if you know the level of noise, the standard deviation of noise, I can tell you what the finite difference interval should be, so that the finite difference approximation will give a good approximation to the function. So here's an example. The function is smooth. Now we put uniform noise to that. And on the left is a finite difference based on the right finite differencing interval, large enough. Here is a finite difference based on too small an interval. So you're differentiating the noise. There's going to be a procedure invented by one of the great computer scientists a long time ago that is going to tell us how to find this interval, right? But do you agree that that red line is a good representation of the gradient? And this is a disaster, right? So is it going to be possible? And that's what we're going to do in our algorithm, do that estimation. Okay, so the person who came up with this idea, some of you have recognized the name, is Hamming. Hamming, the famous Hamming from computer science says, do the following. In order to find out the finite difference interval, look at the point where you are, take a random direction, and evaluate the function, say, 7 times there. Not many times, independently of the dimension of the problem. Take a random direction, evaluate the function, say, 7 times along that line. And then perform differences of the values that you have seen. Okay, so this is the value of the objective function at those points. I plot them there. And then I plot the difference in the function values, which is more or less the derivative. So this is the difference of those two values, and that's the difference of those two values. This is the table of finite differences. And then do it more. Then you take the differences of these differences and you put them here. So you create a table of differences, and this table finishes, right? Because at some point you run out of that, right? Now, these numbers really should converge to 0. Why should they converge to 0? The second difference divided by h squared approximates the Hessian. But the second difference not divided by h squared should converge to 0. So if you observe this table and the numbers do not go to 0, means that you're differentiating noise. And so you see that the values here are pretty constant. At this point, what I'm doing, I'm differentiating noise. And that's enough for me to know to extract information from these columns based on a formula that he developed. Actually, it takes only a few minutes to derive. We look at these values here, which are sort of weighted averages of the columns. We look at them and see if they change. When they don't change anymore, this gives us an information on how to compute the finite difference interval, which is, sorry, not the finite difference interval. It gives you an idea of the noise level, sigma. So this is, T means column. Some weighted average of that gives us the standard deviation of the noise. And then with the standard deviation of the noise, you're going to plug it into the usual formula. By the way, I should explain, why did Hamming write a program in order to determine standard deviation of noise? Well, this is classical computer science. Computers were all over the place. They had different kinds of precision. He wanted to write a program that would detect machine precision for any number. And that's a very reliable way to do that. But what's interesting is that Moret and Wild at Argonne said, you know, this is not just for finite precision is a way of noise. This is valid for any type of noise. And we picked up on that. And once you have it, the noise level, the formula for the differencing interval is has very simple forms. Just plug it in, you know what the finite difference interval is. And then we go one step forward. If you really have simple approximations to the gradients, why not use a quasi-Newton algorithm? Why not create a quadratic model that approximates the function? We do that here. And this is an idea that just continues to survive, this idea of quasi-Newton methods, just continues to thrive. People think like, you know, we talked about them, and then they come back. For general non-smooth optimization, quasi-Newton methods is currently considered the best algorithm. Here in this context, you only have function values. With that, we estimated gradients. Once you have these decent gradients, put them into a quasi-Newton algorithm, if you know what they are, they will construct a quadratic model that is scalable. And this LBFGS algorithm is of order D. So we did those computations. Here's the algorithm. And it works fairly well. The red line are our friends, Powell and Katya, the state-of-the-art in derivative-free optimization. And here are two versions of our algorithm, Albert Barajas' algorithm, forward and central differences. And it's working really well. This is in terms of function evaluations. In terms of total computational work, it's even more benign, because their work is d to the 4 and our work is OD, right? So this is a good thing. It worked really well. But I'm not going to use that for reinforcement learning. Reinforcement learning is too noisy. I'm going to use very, very crude approximations. So our latest results show that if you use, now I see that this thing got perturbed. And here are the typical problems for the Mujoko set. I run those problems there. And when I run them with Gaussian smoothing, using a very crude approximation to the derivative. And this is what we observe. This is Gaussian smoothing by doing, at every point, just evaluating one random direction, doing the differencing, and declaring that to be the gradient of the objective function. This is an extremely weak gradient. That's this line here. This line over here is full finite differences, computing the real gradient. As with neural networks, it turns out that the very noisy approximations to the gradient are working better, are giving you better results in that. Right? So I want to summarize what I said here. So multiple results about this. By the way, this area of reinforcement learning, of course, it seems to be in its infancy, right? The more I dig into, you're optimizing these functions, are they actually continuous? Are they actually, could they be discrete? What the sampling does on that. People are just throwing algorithms on them and getting results. And when I was saying, I don't know how to optimize a function in many, many variables with only function values, nobody's saying anybody's optimizing anything, right? They're decreasing the function value. And it's a complicated thing. But it was a good thing to contrast two different ideas that came from two different disciplines about how to do derivative-free optimization. So the takeaway is, if you have only function values, estimate derivatives. If you have noisy function values, estimate derivatives. Once you have estimated derivatives, give it to the gradient method. Give it to a quasi-Newton method. I think that's the way to go. All right, thanks.
All right, so we have quite a lot of time for questions also. So can people raise their hands who have questions, and you'll get a microphone.
Hi, how do you cope with noise with long tails in the distribution?
Yeah, very good. You caught me cheating there. The only analysis that we have so far for the algorithm I presented is for the case where the noise is bounded. Now, if I have tails, what would I do? If you were to work with me on a project, let's do it together. Let's look at unbounded noise. There are two possibilities. I'm going to design an optimization algorithm that can handle that, or we're going to filter out outliers. We're going to find a procedure that says don't use that information. I would go for the latter. I would take what we have here and try to see how we can get, sort of Gaussian noise would give you this, right? But that was a very good question. He caught me there.
I actually have a question. So I'm wondering, because since you're doing finite differences, so as your dimension grows, I mean, practically this could become very expensive. I was wondering how this compares to, for example, using expected improvement where you have a Gaussian process, for example, fitted. And it also, I've seen that it works with noise, and then, I was wondering in your comment on that.
I think there's no cheaper way to do that. If you do Gaussian smoothing, which is a randomized process, you really have to do a lot of those random directions, right? Finite differences is. I think by nature, this problem requires in general, unless it has structure, a lot of function evaluations. Now, there is one thing, if I can say, that I should have said at the beginning of the talk. General optimization problems, nonlinear, are really hard to solve unless there's a low-level structure of the problem that makes it possible. Almost everything that we solve, when you look at the Hessian matrix is almost low rank. There are subspaces. And that must be the case with neural networks, because otherwise you wouldn't get anywhere with that, right? So once you have only function values, you cannot discover those manifolds. So unless someone would tell you, sample in a certain way, if you have that knowledge, then you can do it in much less work. But the black box system, you cannot do it. You have to pay that tremendous price in order to get there. By the way, if I can finish just with one thing, because it is funny, now that I'm so close. I mean, I studied just there. So I was an undergraduate in physics here, theoretical physics. Fun, right? But my brother and I used to build stuff. And we built a telescope. You know, one of those things that you build everything. You grind the mirror and you know, everything. You put it all together. And we were having fun with the telescope. We would drive out of Mexico City so there wasn't, you know, you could see something, and our telescope would tell us pretty good stuff. And then when I was a student, I heard the Astronomy Institute here has a really good machine for grinding mirrors, right? And then I said, well, they should really grind my mirror, right? How do I do this? And so I thought, well, the only possibility is actually to volunteer to be an intern with the Astronomy Institute. So I interned with them. And after a little while, they agreed to polish our mirror. But what happened is I had to do some work, right? Mirror, you don't just go there. And my work was actually to work with a ray tracing program that they had at the time. They were designing a telescope, Ritchie-Menier type, that has both mirrors and lenses. And the idea is to minimize aberrations, chromatic astigmatism, to optimize the quality of the image. And they had a program that had come from Kodak, the ray tracing, and then you do the optimization. And then I thought, oh, this optimization sounds pretty good, right? I started looking at that optimization. I've never stopped looking at optimization since then, just because of this telescope, right?
Hello. Would you say, for example, when you have like this ray tracing or a light thing, the way like the noise that light makes, it's like a Gaussian blur, I guess, or something. So would like modeling that but running it with lenses, that would be like almost immediate, right? Like that calculation. So is there like with this optical focus, like doing optimization?
Oh yeah. In fact, the reason why you have cameras that are so good and so small is because it just got better and better, the optimization. I mean, it was just a matter of finding out how to exactly find the shape and get the materials, right? So it's just, this is all just 30 years.
Yeah, but I mean, like, you have only one lens in this stuff, like making a neural network with every Gaussian node, having it like a lens, and yeah, when you run, it goes like really fast, right?
I hadn't thought about this. So you want to run inside a neural network. Part of the operation is the ray tracing.
Yeah.
And you're going to combine it with this inner products and ReLUs.
I mean,
I have to think
doing the lenses is really expensive, right?
Yeah.
So, but that would be like some sort of like not neural network, but like optical network that does the calculate. Well, I mean also like measuring the light. It's also like a expensive problem. I mean, to get the samples.
I think you're into something here, and I bet in the audience there are people who know much more about optics. Yes, hi.
So, just to answer your question, sorry. In MIT, Dirk Englund is a professor that uses SLMs, these light modulators, to try to solve this type of optimization problems. And they have a startup company, I forget the name, that raised about $20 million to try to do something similar. So you should check that out. Yeah.
Thank you.
I have a second question, actually. I'm taking advantage of that. Since you're getting the Hessian approximation with the BFGS, there are some techniques that you can do to get, so instead of doing finite difference in every direction, you can do like conjugate directions, and then have you looked at this again for efficiency in the sampling? Or
conjugate directions are expensive, right? In general, if a function is quadratic, you can get conjugacy by just doing a dot product every time. Once you go from quadratic to non-quadratic, the concept of conjugacy is not well defined, and the nonlinear conjugate gradient algorithm is not that stable. So after so many years, we found out this is quasi-Newton approximations because they have some certain overriding properties. They're very efficient. So what I mean is by the following. If you want conjugacy, which means that you want to find the basis, if you get error, even rounding error, destroys your basis. Now, if you have adversarial situations where the objective function looks like this and then it turns, then your conjugacy is going to go out the drain, right? In a quasi-Newton algorithm, if I move from here to there and tells me that the function looks like this, and in the next step I move along the same direction, tells me the function looks very different, the last update overwrites the first update. So you don't have to combine them all together and create a basis like this. This is a very generic type of answer. Yeah.
All right. There's no more questions, and let's thank Jorge Nacelada again, please. All right, so now it's time for lunch. So we have 1 hour. We'll be back here at 3. So there's lots of places you can go to lunch, just in general. Grab your favorite person that knows UNAM a bit well, and there's lots of places around when you can go and eat. And let's be back here at 3, please. Thank you.